I think yes, so I think everything is fine. So should we go ahead with the proceedings of the lecture? Yes. So I hope all of you are doing the revision part, and I think as I discussed in the last classes, last sessions too, in the GATE score booster sessions also. So this is the time when you guys should focus on revision, don't learn new content, right? So revision is one thing that you have to focus, or you should also attempt all the previous year questions. So just keep on practicing the previous year questions and the mock test series. So this is the time when, you know, whatever you have learned, it is the time to gather that and just prepare it so that you can attempt it in the exam, right? So don't focus on new content. So today in this session, what we are going to do is we are going to revise the entire theory of computation. We'll try to cover all the basic concepts, and we'll also try to do certain questions on theory of computation, but majorly the focus will not be on questions. The focus will majorly be on attempting trying to understand what are the basic concepts and just revise through all these concepts, right? We will not focus, because in the GATE score booster sessions, what we focused on the questions. Right now the focus is to take you through the entire course within the next 3 hours, 3.5 hours. We'll try to keep the session till 8:15 or 8:30, that much time we'll invest. And in that much time, what we are going to do, we are going to rush through all the concepts of theory of computation so that everything is on tips, right? So that is the purpose of today's session, right? So yeah, so let us start the session. So is everyone clear about the agenda? So the agenda is to go through all the concepts of theory of computation so as to summarize theory of computation within 3 hours, right? The major focus is not on questions, the major focus is to revise everything that we have already gathered in the classes, right? So what we learned in around 60-65 hours, we'll try to summarize that within 3.5 hours, right? Is it okay everyone? Just let me know, is everyone fine with the agenda or not? So Abhilash is there, Kundan is there, Ayush is there, Jay is there, right? So yes guys, okay, good. So so as I usually do in my sessions, can you guys just let me know what is basically theory of computation? So I think we'll start with the basic meaning of theory of computation, and then we will decide the agenda of today's class, today's session, so that what are the things that we need to revise in theory of computation. So first of all, tell me, what is theory of computation? What is theory of computation? Right. So what is theory of computation? So whosoever knows the meaning of theory of computation should reply. So what do you guys think? What is theory of computation? It is a subject in computer science, that I know. But tell me, what is the purpose of studying theory of computation? What is its importance in computer science? Yeah, any answers? Yes guys, what do you think? What is the okay, so Abhilash is automation theory. So Abhilash, what you did is you told me just, you know, it's just like I'm catching my ear from this hand, and then you just caught it from the other hand. That's it. So that is not the meaning. What is the meaning of theory of computation? What you are saying is, you are saying it as automation theory. It is the same. I can call it as automation theory also, but what is the real meaning of theory of computation? And why do we study it? So Ayush is the branch that deals with computation or problem solving with the help of computation. To some extent it is correct, but not up to the mark, Ayush. Not up to the mark. So what else? What do you think, Jay and Kundan? What do you think? What is theory of computation? What do you guys think? Yes, Ayush said something, but what about Kundan and Jay? What do you guys think? What is theory of computation? Yes, guys, any other answers? No other answers? Okay, I'll say now. So Jay and Kundan, please keep on participating in the discussion, because that way things go more smoothly, and I get to know how much I have to speak, right? So just let me know what do you think. If you don't think anything, just say, sir, don't know. We know theory of computation, but we don't know what does it mean. Even that is fine. That is for what I am here to discuss. So what are your opinions, Jay and Kundan? Okay, so let me tell now. So basically here we are discussing about, so in theory we are going to model. So we are going to study the models of computation. So what do I mean by models and what do I mean by computation? So whatever a computer can do, whatever a machine can do, that is what we are trying to understand that through a model, right? And we are trying to understand the power of that model, right? So basically the basic purpose is to understand the power of the various models. And what are the various models that we have? The various automata that we have. So we have finite automata, we have push down automata, we have linear bounded automata, and we have Turing machines as far as the GATE syllabus is concerned. So there are other automatas also like bouquet automata and so on and so forth, which you will study in your masters when you go ahead for it. But at the end of it, as far as the GATE is concerned, we are going to study the power of the various models of computation, right? So through this we'll try to understand that what a modern machine can do, what a machine can do, what is it that a machine can do, what is it a machine cannot do. So that is what we are saying, the capability of a machine or the power of a machine, right? So for example, there are certain things that a finite automata can do, but there are certain things that a finite automata can do. So what is the limitation of a finite automata? That is what is basically that all study is because of this theory of computation, because we are trying to model the behavior of the computation, right? So model the computation, right? So basically then comes push down automata. In push down automata also is able to capable of doing certain things and certain things it cannot do. So that is where we are going to study the limitations of push down automata also, and so on for linear bounded automata and Turing machines. So basically this entire branch deals with the modeling of the computational devices. We are going to model them and we are going to understand the power of these machines, right? Is it now okay, guys? Abhilash, Ayush, are you getting the point? Jay, Kundan, now I think since I have applied, you can just let me know whether you understood the point or not. And others, if they have joined also, please comment and then let me know, so that I get to know you are on the same page, and then go ahead. Then I can go ahead with the next point, right? Good. Good, Abhilash. So what about Ayush, Jay and Kundan? Are you getting this stuff or not? Yes. Yes, Snehal. Okay, good. Good, Snehal. So now I think let us first of all understand what are the things that we have in syllabus and what is their weightage. What is the weightage of each part? I discussed briefly in score booster, GATE score booster sessions also, but here I'll again repeat that part because many people might be new to the thing. So I'm just briefly telling you that what is the expectation with each part in the coming GATE examination, right? And this is just all probabilistic. I am telling you which are higher probabilistic topics to come in the exam, right? So what do you guys think? Abhilash, I think you were there in the session. Can you tell me what are the things that you think are the most important for the coming GATE exam as far as the TOC is concerned? As far as TOC is concerned. Yes. Yes, guys. So first thing which is very important is basically the identification of the type of the language. Identification of the language class. This is one of the most important topics that you can expect, and just mind you that this is basically in the last GATE exam, GATE 2022, there were around 2 questions directly from identification of the class of the language. So this is what from this you can understand the importance. And if you go around and look at the last like 6 or 7 years papers, you will find at least 10 to 12 questions on that. So that shows that at least 1 to 2 questions are definitely going to be there in this on this topic. Now, the second most important topic is the decidability properties, and the closure properties. Right? And you can expect almost, just a second, you can expect almost 1 to 2 questions from this. So this is minimum and this is maximum. Then 1 to 1 questions on decidability, 1 to 1 questions on closure properties. So this is one thing. Then Abhilash also talks about classification of the language, decidability and closure. Right, Abhilash, these are the most important topics. Very good. And also about regular expressions. So regular expressions also you will find a lot many questions, and on an average at least 1 question is always coming on regular expressions. So this is also another important topic which you should definitely cover. And there is a probability, there is higher, so when we are making questions on regular expressions, it gives us the freedom to make more and more MSQs. And as you know, as far as computer science is concerned, the number of MSQs is increasing in the GATE exam, right? So regular expressions is also another important thing that we have, and all other topics. So this will make us at least 4 questions are coming from this much, and then the remaining topics, all other topics, we might get 1 to 2 questions. So overall we will get around 4 to 6 questions from TOC. So what are other topics, guys? What are other topics in theory of computation? What are other topics? Yes, guys. Abhilash, Snehal, Ayush, what are the other things that we study in theory of computation? So we talk about DFAs, we talk about NFAs, we talk about epsilon NFAs, we talk about PDAs, we talk about Turing machines, and so on. And we also talk about grammars, right? So all this, you might find 0 to 2 questions. So 0 to 2 questions from this part. So roughly you will have 4 to, I should say, 7 questions from theory of computation. So this part is roughly, so sometimes 2 questions will come from here, or 1 from here, or sometimes 1 from here and 2 from here. So roughly 4 to 6 questions you can expect from theory of computation, or at max 7. So this will be roughly the weightage of the various parts. And yes, Tanish, grammar is also important part which might be asked in the exam. Very good. So I think all of you have a very good idea that what are the things that are there in theory of computation as far as the GATE syllabus is concerned. Although theory of computation is a very, very vast subject, there are various kinds of automata that have been invented from time to time. For example, we have bookie automata, we have timed automata, and so on and so forth. There are so many other types of automata which you are going to definitely study if you go to, so once you join your master's program, right? So if you are aspiring to join the master's program, right? So then Tanish says grammars, Ayush says in TM and regular languages, DFA, NFA, PDA, RES. Yes. So all the topics almost I have covered over here, and today what we will do is, whatever I have written on this board, we'll just go through all these points so that we all of us are on the same page before we go to the exam, right? So all this needs to be brushed up, and that is what we are going to do in today's session, right? And this session will go on for at least till 8:15 till 8:30. We'll revise everything, whatever is there in the syllabus, right? So that's all about the agenda of the today's session, right? So yes, and I'll keep this session interactive, you know, I'll keep on asking you guys questions so that I just keep on checking that whether you guys remember the stuff or not, and then I will keep on emphasizing the most important points throughout this session, right? So I'll keep on checking whether you remember the things or not. So just be interactive. So, and to make this session more and more interesting, right? Okay. So let's talk about first of all about DFAs. So okay guys, so what is a DFA? What is a DFA? It stands for deterministic finite state automata. Deterministic finite state automata, right? So now you guys tell me, what is the quintuple about of deterministic finite state automata? So what is the quintuple? So first of all, before we go there, just tell me why it is called deterministic finite state automata. So finite state because the number of states are finite. Can you guys tell me why it is called deterministic? Why do we call it as deterministic finite state automaton? Why we call it deterministic finite state automaton? So Abhilash, okay, that is you are okay about the quintuple, and but why it is called deterministic? Also let me know about it, right? Yeah. What do you think? Why it is called deterministic? Yeah. So why it is called deterministic? So Adish is also here. Adish says because each symbol on a state has only one transition. Okay. Adish, only one transition? No. Just check whether you are saying what you are saying is correct or not. Just cross check. Every state will have just one transition. There might be more than one transitions, right? One transition on what? Each symbol on a state. Okay, so you have also mentioned that because each symbol on a state has only one transition. Very good, Adish. I didn't read the beginning of your expression, right? Okay, yeah, correct. So, correct. When you said this, it is definitely correct, Adish. So, and Mayank also, we know at each state to move to one on any input. Okay. So why deterministic? I'll just let me now tell it. I think many of you know it very well. So this is deterministic because on every state, on every symbol, you are going to exactly one state. Neither you can go to more than one states, or neither you can do this that you go to more than one states, nor you can decide to not go to any state. So you have to go to exactly one state. So that is why it is called deterministic finite state automata, right? And finite state because the number of states are finite, right? Okay. So one state has one transition for each input. Yes, Abhilash, you are definitely correct. Now guys, tell me what is the quintuple? So this is basically the delta, the transition function of the deterministic finite state automata. This is the transition function of deterministic finite state automata. Okay, so right. So now let us talk about the quintuple of the deterministic finite state automata. Can you guys tell me what is the quintuple for deterministic finite state automata? Abhilash has already replied that, but what about others? Do they remember or not? Just let me know the quintuple for deterministic finite state automata. So it is basically Q, sigma, delta, Q naught and F. Now what is Q? It is basically the set of states that we have. So the set of states is basically Q. Set of states is basically Q. Sigma is basically, so sigma is basically my input alphabet, which is also a finite set. So again, mind you that this representation has to be finite, because if this representation itself is infinite, there is no point in making the automata. So why, guys, so before we go ahead, just let me know, why do we make automata? What is the main purpose? Why do we make automata? What is the main purpose of an automata? What do you guys think? So come on, guys, keep on replying, because you have studied this subject at least in your colleges too, at least, and also in the IMS GATE Academy too, or maybe if you are not from IMS, you must have attended it somewhere else, but you should know the basic motivation. Yeah. To learn the computational power of a machine, Abhilash, that we have done. But what does an automata do? So given an automata, what it does? What is the use of that? What is the use of that? So what is the main purpose? To check a language belongs to the language, to check, yes, definitely, very good, Abhilash. So we have to check whether the given string belongs to the language or not, right? That is the purpose. And since the language is infinite, what I am trying to do is I am trying to give a finite representation of the language. Now this is a finite representation of the language that can be stored inside a computer system. Because my language is infinite, I cannot store that I cannot store that language in the computer system and then on the runtime check that whether the string belongs to the language or not, right? I cannot do that for an infinite language, right? Are you getting this point or not? So why I am doing so? What I am trying to do is I am trying to make a finite representation of the language, and the computer machine will run this on this automata, will run the string on the automata, and then finally tell you whether the string is accepted or not. So that is given a language, I'll make an automata for it. So given a language, I'll make an automata for it, and then I'll give a string to the automata, and it will tell me whether the string belongs to the language or the string does not belongs to the language. So that is the basic purpose. So that is the basic purpose of making the automata. So what is important here is, since the language is infinite, I cannot store that into the computer, but the representation which I am going to make has to be a finite representation. If that representation is also infinite, then it becomes a chicken egg problem, right? So you wanted to solve one infinity problem, you ended up making another infinity, right? So therefore that representation has to be finite. So everything which you see in this is going to be finite. So for example, Q, the set of states are going to be finite. Sigma, the input alphabet, is going to be finite. Delta is our transition function which I have already defined. What is Q naught? What is Q naught? Q naught is the initial state. There will be always one initial state, and then finally I am going to have a final states. So this is set of final states. Set of final states. So how many final states I can have? Final states will be a subset of Q. I can have more than one final states also, right? Is everyone clear about the quintuple? If there is any confusion, please do let me know so that I can stop here and then take your query and then move ahead on the next topic. So what I have planned in my mind is that every topic we are just going to quickly brush up the topic and do at least one question on every topic, so that everything gets brushed up properly, right? So yeah, so is everyone okay with this notation? Everyone okay with these notations? Yes, guys, please do reply so that I get to know whether you are on the same page or not, and can I move ahead or not. Yeah, Adesh, is it okay? Yeah, okay, good. So now let us solve one question on DFAs, and I think this is a very good question which will cover almost all the concepts which we should keep in mind while making DFAs. So right, so the question goes like this: construct a minimal DFA DFA which accepts set of all strings over sigma is equals to a comma b such that every a is followed by a bb. Every a is followed by a bb. And then you have to tell me the percentage of final states in this automata. Instead of that, just tell me the total number of transitions, total number of transitions in this automata, in this minimal DFA. Tell me the total number of transitions in this DFA, right? So what we'll do is we'll just solve this question and we'll quickly revise all the concepts that needs to be kept in mind while making DFAs. Yeah. So you have just some 2 minutes to solve this and then I'll solve it for you guys. So Adesh, your answer is incorrect. Just cross check once. Just cross check once. Yes guys, what are the answers? So Adesh, can you please cross check your answer? It should not be 10. It should not be 10. Yes, Mayank, you are 100% correct. So Abhilash, what is the answer? It should not take more than 2 minutes. It's already been 2 minutes. Yes, Kirti, you are correct. Very good. So how is the preparation going, Kirti? Yes, Abhilash, you are also correct. So Adish, are things working fine? We discussed the plan in the last My Plan session. Things are working fine. Is it working? And I think the same goes for Abhilash also. We also discussed about that. Yeah. So just let me know your status also. Is everything working fine? The preparation is going on smoothly or not? Yes, yes, just a second. Okay, good, good, Abhilash. Yeah. So in case again, guys, if there is some other confusion, we can always have a. Yes, sir, I'm trying to. Okay, okay, Adish. Don't worry. So things will go on smoothly. Just last 21 days are left. We have to just remain focused in these 21 days. And if there is any issue, we can always have a discussion in my plan session. We'll again discuss if something needs to be some tweaks needs to be done in the strategy. We'll definitely discuss again. Okay. So let's go back to this question, and I think almost all of you have answered it correctly now. So Adish, just cross check once. I think there is one small mistake. Okay. So anyways, we'll take this example itself and try to draw the DFA. So over here, so what is the first thing that you have to keep in mind while making the DFAs is, first of all, try to understand the language. So try to understand the language. So it says that every A has to be followed by a BB. So first step should always be is to understand the language that you have at hand. So tell me guys, is epsilon a part of the language or not? Is epsilon a part of the language or not? Yes. So epsilon is there in the language, yes. Then we have single b is also there, two b's are also there, and b raised to power n is also there in the language, because the condition is only on a's. As long as b's are coming, there is no issue, right? And after that, we might have an a, but that a has to be followed by a bb and so on. So then that is basically the language, and we see that this language is infinite. So always while making DFAs, keep two things in mind. First step should always be to write down the language and always take care of epsilon. You know, most of the questions that will go wrong is just because we do not consider epsilon, which is a very important string that needs to be checked, right? Yes, Sapta, good afternoon. Yeah, so always check about epsilon. Never forget about it. And then next step should be, so I think these are the two important points that you should keep in mind while attempting the questions in the GATE. Okay, both pens have become green. Let me take a yellow. So this is okay. This is okay. Yeah. Okay. The third thing is to draw the automata for the smallest string in the language, right? So therefore, the smallest string is epsilon. So epsilon belongs to the language. Epsilon belongs to the language. Just a second, guys. Epsilon belongs to the language. Okay. So epsilon belongs to the language. So therefore, the initial state has to be the final state. That's the first thing that we should keep in mind, right? Now, since epsilon belongs to the language, and then after that we know that any number of b's also belongs to the language, so therefore we'll put a loop on b. Now the next smallest thing that is there in the language is a, b, b. Let us make the automata for it. The automata will look like this, right? Right. So this is the third step that you should keep in mind. Draw the automata for the smallest string in the language and then try to complete the automata. So those who have got 8 transitions, just wait for 2 more minutes. I'll also get 8 transitions. Don't worry. I have made this purposefully because these steps should be there in your mind while attempting the questions on DFAs, right? So any number of b's is in the language, epsilon is in the language, and then a, b, b should also be in the language. Therefore, I have made the automata for that. And then the next step is to complete the remaining automata. Whatever is left, just try to complete the transitions, right? Because we know since it is a DFA, we will have deterministic transitions on every combination of q cross sigma, right? So therefore, We know what happens on this state on a B, we know what happens on this state on an A. Now we have to calculate what happens on this state if an A is followed by an A. So then we go to a dead state, because every A has to be followed by a B. So if A is followed by an A, therefore it will go to a dead state, right? So A will be, if A is followed by an A, we will go to a dead state. Now so we have completed the transitions for this state also on A and B. Now for this state, what happens if an A comes? Again A has to be followed by two B's, but A is followed by a B and then followed by an A again. Again the trend has been broken, so we'll again go to a dead state. So we'll again go to a dead state, and therefore we have completed the transitions for this state on A and B also. Now the last state is the final state. We have to decide what happens if an A comes on this state and what happens if a B comes on this state. What happens if a B comes? Any number of B's are always fine. The only problem is with A's. So therefore we'll remain over here. Now if an A comes, then again we have to check it has to be followed by a BB. Which state checks that? This state checks it. So we'll go over here. So this way if we calculate, we'll get 10 transitions, but this is not okay. So what is the mistake, guys, in this automata? What is the mistake? I have got 10 transitions. This is incorrect. What is the mistake? What is the mistake, guys? Tell me. So those who have got 8 as the answer should tell me. Why 8 and why not 10? Not minimal. Very good, Abhilash. Very good. So now, as I said, the first step is to write the language. Second step is to consider about epsilon, is to think about epsilon, whether it is there in the language or not. Third step is to make the automata for the smallest string in the language and then try to complete it. This is the third point which you should keep in mind. Now the fourth thing is, think that about that whether each state has a unique meaning or not, or can we minimize the things or not. Now if you closely observe this, you will find that this state and the first state has similar behavior. State 1 on B remains on itself and it is also a final state. Last state also on B remains on itself and it is also a final state. Then on A, both the states go to this state. So let me name the states also. This is Q0, this is Q1, this is Q2, this is Q3 and this is Q4. So Q0 and Q4 have similar behavior. Both on A are going to Q0, Q1 and both on B are remaining on themselves and both are final states. So why not merge these states? So instead of making all this, what I can do is, so what I can do is I can merge this state with the initial state, and on B I will directly go to the initial state. And this way I will reduce this automata to a smaller one, right? So what we will get now here is 8 transitions. Since there are 4 states and there are 2 transitions on each state, the answer will be 8. So always remember the 4th and 5th step, that each state should have a unique meaning. And then see if some minimization is possible. So if you keep all these 5 points in your mind, you can never commit a mistake in the DFA based questions, right? So this state represents all the strings, epsilon, A, ABB. So let me write it this way. So this state contains all the states, epsilon, A, ABB, single B, all B's, everything is there. Now this state contains, whenever the pattern is broken, whenever A is followed by an A, or A is followed by a BA, or A is followed by double A, and so on and so forth. So this state represents that. Now what are these states representing? We have got a single A, and over this state represents we have got an AB, right? So every state should have a unique meaning, and then finally you should see that whether you are able to merge or not. So that's all about DFAs, and I think this much revision is more than enough for a DFA. If you keep these 5 points which I just discussed in your mind, like writing about the language, thinking about epsilon, making the DFA for the smallest string in the language, and then completing the DFA, and then think about the meaning of each state and see if some minimization is possible. If you keep all these 5 points in your mind, then definitely there is no chance of mistake in the questions related to DFAs, right? Okay, so many of you have required it correctly. Abhilash says not minimal, Saptak says not minimal, Souvik says last final state is not required, and then we can draw the transition to the first state, right? No need, and Saptak also says clear, sir, right? So is everyone clear till this point? Should we move ahead to the next topic? Should we move ahead? Yes, guys, do respond so that I get to know. Yes, Abhilash says okay, Saptak says okay, Adesh is also okay. Good. So now let's talk about minimization. So how do we do the minimization of a DFA? This is also an important thing to be discussed. Okay? So how do we do the DFA minimization? How do we do that? So how do we do the DFA minimization? So just 1 minute to you guys to reply. Briefly the process. I don't want the detailed algorithm. I'll discuss briefly that. But what do you guys think? How do we do the minimization? Right. Good, Souvik. What else needs to be done? Yes. Maybe just the pointers are okay. Right? And then Mayank is 100% correct. What else, Mayank? Yes. Yes, divide states. Okay, so let me say it to you guys. So first of all, the first thing that needs to be done is remove unreachable states. So this is a very important step, and always keep in mind while checking about the unreachability of the state, what you have to keep in mind that you have to check the unreachability by drawing the DFA. Just don't look at the transition table and try to find out that these states are unreachable, right? Just try to make the DFA, and then only you will realize that what are unreachable states, right? So this is one thing that you should keep in mind. Second thing is, make two set of states, final and non-final. So these states are basically called zero equivalent. What do you mean by zero equivalent? That their behavior is same on without taking any input, right? Yes, Kirti, very good. And what else we have to do? We have to make two set of states, final and non-final. These are zero equivalent states. Yes, very good, Adish. Remove unreachable states, divide the states into finite and non-finite, and then combine the states if the transition are two similar states. Not combine but divide, right? Then on each alphabet, check the behavior of the sets. Check the behavior of the sets. Check the set behavior of each state. Check the set behavior of each state. Behavior of each state on sigma and split if the behavior is different. Split if the behavior is different. And in this case, what you get is one equivalent. In this case, what you are going to get is one equivalent. Okay? So check the set behavior of each state on each sigma and split the behavior and split if the behavior is different. Sorry for the typo. And split if the behavior is different. Split if the behavior is different. Right? And these states are one equivalent, and keep on doing this. Keep on doing this until the things stabilize. Until the things stabilize. I should say sets. To be technical, it should be sets. Until the sets stabilize. Stabilize. Right? And how would you construct the transitions? How would you find the transitions? Yes. So guys, how would you find out the transitions? How would you find out the transitions? How would you find out the transitions? Yes. How would you find out the transitions? So by doing this, if the thing stabilize, you are going to get the n equivalent. That is, on n length inputs, these states have the same behavior. On n length inputs also, these states are going to have the same behavior. So now tell me how you are going to find out the transitions in this minimized automata. How we are going to find the transitions in this minimized automata. So for that, refer the original DFA. Refer the original DFA to find the transitions. Right, that's all about the procedure of DFA minimization. That is all about the procedure of DFA minimization. Right? I hope you could quickly go through quickly revise the DFA minimization concepts. Let's do a short question on this and then we'll move ahead with the next topic. Till this, is everybody on the same page or not? Tell me guys. Is it okay or not? Yes, so keep interacting and keep on letting me know that is everything fine or not. Yes, Sovik is okay, Abhilash is okay. Yes, good. So now let's do a small question on minimization. Okay. So I am giving you the transition table. Okay, just try to minimize this DFA and then we'll go ahead with the next topic. Right. Just minimize it in next 2 minutes. So just 2 minutes to you to solve it and then we'll move to the next topic. So how many states you are going to get into the minimized DFA if you take this? So Abhilash, it should not be 6, just cross check once. Souvik says 5, even 5 is incorrect, Souvik. 5 is incorrect. Just last 30 seconds and then I'll solve it. What is the answer, Kirti? Mayank? Mayank is okay. Very good, Mayank. Kirti and I think others are also there. Saptak. What is the answer, Saptak? Saptak is also correct. Very good, Saptak. Souvik, Abhilash, just cross check your answers once. Okay, I think enough time has been given and let us see the answer now. So Abhilash, yes, very good, Abhilash. So I hope you realize the mistake, Abhilash. The first step has a meaning. That means that what you have to do is you have to remove the unreachable states first of all. Abhilash, I think you made the same mistake. Yeah. Okay. So let me just draw the DFA and then after that you know how to do it, right? So this is Q naught. So initially we have Q naught on A goes to Q1. This is also the initial state as well as the final state. On B it remains on itself. Q1 on A goes to Q naught. On A it goes to Q naught. On B it remains on, it goes to Q2, right? So Q0 on A is going to Q1, Q0 on B is going to Q0 itself, Q1 on A goes to Q0, and Q1 on B goes to Q2. Q2 on A goes to Q3, Q2 on A goes to Q3 say, and Q2 on B goes to Q1, right? So Q3 on A goes to Q3 and B goes to Q0. And the remaining states, if you see, that is Q4, Q5, Q6, Q7, they are a closed set and they are unreachable on the whole. So let's see, Q4 on A goes to Q3, on A it goes to Q3, Q4 on B goes to Q5, let's say it is Q5, and then we have Q5 on A goes to Q6 and B goes to Q4, B goes to Q4 and A goes to Q6, and then we have Q6 on A goes to Q5 and B goes to Q6, Q6 on A goes to Q5, B goes to Q6 itself, B goes to Q6 itself, and Q7 on A goes to Q6, okay, Q7 on A goes to Q6 and on B goes to Q3 and on B goes to Q3. Right? And if you see this entire part is unreachable over here, because you cannot reach to this part. And as I mentioned as a caution, that just by looking at this transition table, you will never get to know that what are unreachable states. By this you might have the illusion that only Q7 is unreachable because all other states are coming here. Q0 is coming here, Q1 is coming here, Q2 is coming here, Q3 is coming here, Q4 is coming here, Q5 is coming, Q6 is coming, only Q7 is not coming. So you might assume that only Q7 is unreachable, but in this case only one state, the entire set. Yes, Abhilash, that's the mistake. So that is why I highlighted on this point, I am emphasizing on this point, while removing the unreachable states, always make it a point that you construct the DFA and then do this process. Is it okay, Abhilash? And then do this process. Is it okay? So while applying this, you have to keep this thing in your mind. Right? So entire thing, Q4, Q5, Q6, Q7 is unreachable, and then after that you apply the minimization and the same technique. Right? Once you apply this same technique of minimization over here, you will get that all these states cannot be further reduced. You will get Q0, Q1, Q2, Q3 and Q3. Right? So if you apply that same technique over here, you will all of you will get Q0, Q1, Q2, Q3. Does anybody has any doubt that you will not get 4 states? Then I'll solve it, otherwise we'll move ahead to the next topic. If anybody has a doubt that they are not going to get 4 states, then they can tell me and I can explain. Otherwise, I'll move ahead to the next topic. Okay, everyone? Please do tell me so that I get to know where are you guys, what is the status of you guys, so that I can explain accordingly. Is everyone okay? I mean, clear? Yeah. Okay, good. So let us move ahead to the next one. Then we move ahead to NFAs. So NFA stands for non-deterministic finite state automata. So can you guys tell me the quintuple for NFAs? Quintuple for NFAs. What is the quintuple for NFAs? Yes, yes. Good, Adish, Mayank, Shilpa, all good. Very good. So the quintuple remains the same. So what is the change, guys? Q sigma delta Q naught F, no change. So what is the change in the Q remains the same, that is set of states. Set of states. Sigma is basically your alphabet. No change. Q naught is your initial state. F is your set of final states. There is no change. So where is the change? Change is in delta. What is the change? What is the change? Change is Q cross sigma goes to 2 raised to power Q. Very good. So Q cross sigma now goes to 2 raised to power Q. This is the change. This is the change. Right? So now I can go to multiple states, or I can decide to go to no state, or I can go to a single state. Or I can go to a single state, that is Q cross sigma goes to 2 raised to power Q. 2 raised to power Q is the power set of Q, that is all the subsets of Q. Right? That is the only change that we have it over here. Right? So now you tell me, what is the condition of string acceptance? String acceptance condition in NFA as well as DFA. What is the string acceptance condition in NFA and what is the string acceptance condition in DFA, and how are they different? What is the difference? Yes, thank you, Pragya sir, thank you. So what is the difference between the string acceptance condition of an NFA as or versus DFA? Difference between the string acceptance conditions of NFA versus DFA. Saptak and Souvik must be knowing it very well. So we just discussed yesterday, right? Anyways, I'm just refreshing it for the guys who are going to sit for the exam. But anyways, you guys will also be able to revise. So yes, so Adish says if the string reaches the final state, it's accepted. But in a state, if there is no transition for the symbol, the string is not accepted. Okay, so let me now reiterate this point. Saptak says at least one trace. Very good, Saptak. Very good. So over here, there is only one trace. The one trace should reach the final state. Should reach the final state. And over here, at least one trace should reach the final state. At least one trace should reach the final state. Here, one trace should reach the final state because there is only one trace. That is why that one trace should reach the final state. Over here, there are multiple traces, and we are saying that at least one trace should reach the final state. Is it okay, guys? I think this got refreshed. Adish, is it okay? We discussed this in the class too, right? Yeah. Okay. So now tell me, what is language acceptance condition for NFA versus DFA? NFA versus DFA. What is the language acceptance condition? This is exactly same. This is exactly same. That is, strings in the language should be accepted and the strings not in the language should be rejected. Right? And this is, mind you, this is the very, very important point, and many of the mistakes that are committed by the students in the exam are basically because of forgetting this point. If I say that a regular expression represents a language, if I say that a automata represents a language, if I say a grammar generates a language, then all the strings in the language should be accepted and the strings not in the language should be rejected. This is very important. You can make it a star point, and always, just you have to keep this point in your mind while solving any question in GATE which comes related to the language acceptance or the grammar generation or the regular expression representation. Right? Is everybody clear till this point? Just let me know. Just let me know if everybody is clear till this point. Okay. Right, good guys. So now, just let me just cross check whether you guys understand DFAs or not, NFAs or not, with the help of a simple question. Draw the minimal NFA for strings containing A, and your sigma is A comma B, and what you have to report is the number of transitions. Tell me the number of transitions in the minimal DFA. Right? Just tell me the number of transitions in the minimal DFA. You have some 1 minute to solve this, and then tell me the number of transitions in this minimal DFA. So, okay, what I am understanding is what you guys are doing is counting this as, okay. Yes, Adish is correct. Adish is correct. Others, please check. So what I am assuming is, so while doing this counting, assume that if delta on Q0 comma A is say Q0, and delta on Q0 comma B also A also goes to Q1, count this as 2 transitions. Count this as 2 transitions. Do not count it as 1 transition, and now you tell me the number. Adish, you are correct if you are thinking like this. So what I am expecting is if the delta on Q0 on A also goes to Q0 and also goes on Q1, count it as 2 and then report the answer to me. Assume this and then tell me the answer. Okay, okay, good, good Abhilash. Okay. So meanwhile, those who have already replied, just tell me, why do we make NFAs? We know that every NFA can be converted to a minimal to a DFA. We have an algorithm to do that, that is subset construction. So then why do we do this? Why do we make NFAs at all? So would the world would not have been much more sorted that if the things would have been DFAs only, right? Because DFAs are deterministic, things would have been much more sorted, and world would have been an easier place to live, right? So why do we still make NFAs? Yes, yes, Adish, we are going to discuss. I'll explain the answer. But meanwhile, those who have already answered, yes. So many of you have answered this point correctly. We make NFAs because NFAs are more concise. They are easier to make. So if you make minimal NFA and versus minimal DFA, the number of states might be, NFA will always have smaller or equal states than DFA. So for conciseness, we are doing this, right? And they are more easier to human interpretation. It is easier to make. And you must have realized this while making the NFA for second last symbol from RHS, third last symbol from RHS, fourth last symbol from RHS. If you make the NFA, you will be able to make it within 1 minute. But if I ask you to directly make the DFA, you will take almost half an hour to make that. Right? Is it okay? I think we have discussed all this in class. I am just quickly brushing up the concepts. Okay? So now, let me draw the NFA. So the NFA goes like this. The string must contain an AB. Must contain an A. So I can make it like this. But that way I have 5 transitions. What is it I can do to reduce the number of transitions? Tell me, what is the issue with this? This is NFA 1 and this is 100% correct. But this is not minimal. Can somebody tell me a better NFA for this? Can somebody tell me a better NFA for this? So this way we have 5 transitions. I want to reduce the number of transitions. Can somebody tell me a better NFA? Yes, Adish, you are correct. What about others? How do you guys got 4? Sovik says 4, Saptak says 4. Even Abhilash said 4. Why 4? Why not 5? So what I can do is I can remove this A and I can make it like this. This is also okay, and this way we are going to get 4 transitions. This way we are going to get 4 transitions. Or even what I can do is I can write it like this. Even this way we'll get 4 transitions. All these NFAs are going to accept and represent the same language. And the one which is minimal is these two. These two are minimal and they are having 4 transitions. Okay. So Sovik made 2 mistakes and that's why I got the right answers. So sometimes making 2 mistakes also gives you the correct answer. Anyways. Yes. So, yeah. Is it okay? So now can someone tell me, if I even go further and I remove A from here? If I go further, if I remove A from here also, and I make just this, is this DFA correct or not? Is this NFA correct or not? Or there is some issue with NFA 4? Can I reduce it to 3 transitions? So what is the issue, Abhilash? What is the issue with this? NFA 2 and 3 are correct for sure, but what is the issue with NFA 4, Abhilash? Exactly, very good. Now in this NFA, if 2 A's come, you are going to kill that. You are going to a dead state. That becomes a dead configuration. So for example, in this NFA, you get the string A. This contains A. This should be accepted. Now on first A, you go here. And after that, you have no transition on A. You are going to kill it. You are going to kill it. So therefore, this NFA is incorrect, but these all are correct. So extra A's will be consumed either by this state, or extra A's will be consumed by either by this state in NFA 2 and 3. But in NFA 4, there is no state to consume extra A's. There is no state to consume extra A's, so therefore we are going to have this NFA is incorrect. Right? Is it okay? So this way you are going to get only 3 NFAs, and out of which the minimal ones are these two, and therefore we have 4 transitions if I count the transitions as every transition as a separate transition. Okay? Right? Okay, so let's move ahead. Okay. So on the last A, if I come here, any number of B's are okay. So if it is BAB, yes, good. Yeah, so this is correct. These two are correct, and this is also correct. But so if an MSQ comes in the exam which says that what are out of these, which are the NFAs for this one? All 3 are the NFAs. If it says what is the minimal NFA, these 2 are the answers, right? Okay, so let's move ahead. Oh, I don't want this. Okay, so next comes epsilon NFA. So we know that every NFA can be converted to an equivalent DFA, and we also know that every epsilon NFA can also be converted to an NFA. Then why did we reach to make epsilon NFAs? Was the world not sorted just with NFAs and DFAs? Why did we make this? Why do we have epsilon NFAs, guys? What is the motivation behind making epsilon NFAs? Tell me. Why are we making epsilon NFAs now? Yeah, at least one answer should be there. Then only I'll tell. Or you may, even guess why it is. Guesses are also fine, but at least answer. Okay, always transitions on empty string, allow transitions on empty strings. Yes, definitely, that is, you are trying to define me, what is epsilon NFA, Mayank. And even Souvik is also trying to tell me, so what you are guys telling me is the implication of an epsilon NFA. What you guys are telling me is the implication of epsilon NFA. What I am trying is to ask the motivation. So first of all, the concatenation becomes very easy. So you have NFA 1, you have NFA 2, and you want to concatenate. Just put an epsilon move. You can concatenate them. Right? So concatenation becomes easy, and the second point is, which is even more important, is your again the conciseness improves. The number of transitions are going to reduce, more succinct than NFA. Very good, Mayank. Even more succinct. Even more succinct than NFA. So what is important for as far as the gate perspective is concerned, how to convert an epsilon NFA to an NFA. How to convert an epsilon NFA to NFA. How do we do that, guys? How do we convert an epsilon NFA to NFA? But before that, you have to tell me what is the transition function for epsilon NFA. The transition function is q cross sigma union epsilon to 2 raised to power q. So the only change is this epsilon gets added. Okay. Right. So tell me how we are going to convert an epsilon NFA to an NFA. So let me give you a better question so that you can give me a mathematical answer. So tell me what, so for example, delta dash is the transition function for NFA and delta is the transition function for epsilon NFA. Then tell me what will be delta of q comma a, what will be delta of q comma a, tell me in terms of delta dash, in terms of delta dash, tell me this. If you remember this, this is, you are okay with epsilon NFA and you can easily convert it in the exam. This much refresh, brushing up of epsilon NFA is more than enough. Yes, Abhilash is 100% correct. Very good, Abhilash. So it will be epsilon closure of A, epsilon closure of A, so of Q, comma, delta of epsilon closure of Q comma A, and then take an epsilon closure again, delta dash. If you can remember this, epsilon NFA is sorted for the gate. Right? Is it okay? So you forgot to write delta dash, Abhilash, else everything is correct, right? And I can understand writing delta over here in YouTube is a tough job. But I hope you understand what you are trying to do, right? Yeah. Right? Is it okay, guys? And how do you find out the final states? Just the last pointer. How do you find final states in epsilon NFA? When you convert epsilon NFA to NFA, how do you find the final states? How do you find the final states? So all those states which have, all the states whose epsilon closure contains the final state will be final states. What does that mean? What does that mean? That is, all those states which can reach to the final state using an epsilon move are going to be final states. Right, Abhilash? I think you could not frame it well, but I hope you mean the same. All the set that contain the final state? No, it's all the epsilon closure, all those states whose epsilon closure contains the final state, right? Just yeah, as far as I see, you mean the same thing, but you could not frame it well, right? Okay. Should I move ahead, guys? Tell me. This completes epsilon NFA. This completes epsilon NFA. Okay, good. So just let me know also, Abhilash, Mayank, Kirti, is the pace going fine or not? Is it too fast or is it too slow? I can modulate the pace also. Because since it's a revision session, I am assuming you know certain things. I am not going to explain what is epsilon closure. I am not explaining, you know, a few minor things. Is the pace going fine, Abhilash, Mayank, Sovik, Saptak, and who else was there? Kirti was there. And then I don't remember others. Even this Adish was there. So guys, tell me, is the pace going fine or not? Okay, good, good. So let's go ahead. So now how do we convert an NFA to a DFA? How do we do the conversion? So given an NFA, you want to find out the DFA. How do you do that conversion? What is this method called? What is this method called? What is this method called, guys? Good, good, Mayank. So Mayank has properly revised the notes. Very good, Mayank. Subset construction method. So how is the method? How does the subset construction goes? First of all, remove the unreachable states. Make it a habit that unreachable states are to be removed. Then what do you do next? You start constructing the transition table. Transition table of DFA from the start state of NFA. ठीक है? Then only consider the states which you obtain in the transition table of DFA. So only the states which you obtain in the transition table. You are not going to consider all the states of NFA. Only consider the states which you obtain during the transition table of DFA. Right? What next? Now tell me, now let me ask you a few questions. What next? If delta of Q comma A is phi, what will be delta dash of Q comma A? So delta is for NFA and delta dash is for DFA. Tell me what will be the delta dash? What will be delta dash? Very good, Mayank. It is going to be dead state. And in this case, delta dash of dead state, let me call it D. Delta dash of dead state comma A is also dead. Delta dash of dead state comma B is also dead. Okay, is it okay, everyone? Because how do we define dead state? Dead states are those states which can never reach to final state. They remain on themselves. Right? Now, what next? If delta of, what was delta and what was delta dash? Delta dash is this, okay. So if delta of Q comma A is Qx comma Qy, what will be delta dash of Q comma A? What is it, guys? What is delta dash of q comma a? No, Abhilash, it is incorrect. I am just asking what is delta dash of q comma a? It will be a new state qx qy, because you cannot go to two states in NFA. In DFA you will make a new state, right Abhilash? Are you getting the point? What you are telling me is the answer to my next question, right? You are going one step ahead, Abhilash. So what I wanted to ask is what is delta dash of q comma a? My next question will be the one which you answered. So what will be delta dash of qx comma qy, delta dash of qx comma qy on A? What is this? What is this? Tell me, what is this? Okay, tell me what is this? Yes, so it will be written as delta of qx comma a union delta of qy comma a, and so on. So this you can expand till whatever point you want. Is it okay, guys? Everyone okay till this point? So what's the last point? How to find out the final states? Initial state remains the same. What is final states? What are final states? What are final states, people? Tell me. Yeah, what are the final states? All the states which have any of the final state of NFA. This way you are going to find out the final states. Right? Okay? Yes, Abhilash, Adish, everyone, everything is correct. Very good, guys. Right? So let me move to the next topic. Murray and Mealy machines. So how they are different from NFA, DFA, epsilon NFA? So before we go further, let me tell you, NFA has the power equals to DFA is also equals to epsilon NFA. All of them have equal power. That is, the languages that they are going to accept are all regular languages. They are not going to accept anything more than regular languages. Their power is same. right? Now what is the power of an automata? How do we define the power? What is power? What is power of an automata? Yes, Saptak, you are answering me in the next question, that I am asking you this question. What is power of an automata? So when we say NFA is equivalent in power to DFA, what is it that we are trying to say? Number of languages, exactly. So what are the number of languages that are accepted by the automata is basically the power of the automata, right? And when we say NFA is equivalent in power to DFA, that is the number of languages that NFA is going to accept is equivalent to the number of languages that a DFA is going to accept, and it is also same for the case of epsilon NFA, they are equivalent in power, right? So now let us define Murray and Mealy machines. Murray machines are for output based machines. So the only output that we get from NFA to DFA to or epsilon NFA, it is just the string acceptance. But if we want transducers, that is, they convert the input to output. We get one string as an input and we give one string as an input and we get another string as an output. In that case, we use Murray and Mealy machines, and they are finite automata, they are deterministic finite automata with output. So Murray and Mealy machines are deterministic finite DFAs with output. So when I say DFAs, that is delta function is not going to change, that is q cross sigma to q, this is not going to change, right? So now tell me the 6th tuple of Murray and Mealy machines. Tell me the 6th tuple of Murray and Mealy machines. Tell me the 6th tuple of Murray and Mealy machines. Yes, tell me. What is the 6th tuple? Okay, one more thing is extra in the Adish. Just cross check. What is the extra thing? What is the extra thing? Okay. Right. So the tuple for both of them is same. Tuple for both of them is same, common for both of them. What is the tuple? Q sigma delta Q naught, and instead of F we have another delta and a lambda. So delta is basically your output alphabet, and lambda is the one which is going to map. So tell me the lambda for Murray machines and tell me the lambda for Mealy machines. What is the lambda? What is the lambda for Murray machines and what is the lambda for Mealy machines? What is the lambda? So lambda for Murray machines is Q is being mapped to sigma. Sorry, Q is being mapped to delta. Every state is being mapped to the output alphabet, and over here we are going to map every transition. Here every state is being mapped, over here every transition is being mapped to the output. So this is the only difference between Murray and Mealy machines. Okay everyone? Q cross sigma to delta and Q cross U to delta. Very good Abhilash, very good. Right? Right. Good. So this is about Murray and Mealy machines. Let us draw one Murray machine. Let us draw one Murray machine. So draw the Murray machine which calculates the remainder when a binary number is divided by 5. So draw a Murray machine which calculates the remainder when a binary number is divided by 5. Just 1 minute to you guys to solve this. Sorry, Abhilash. Yeah. Is it okay? Is it audible now, Abhilash? Is it audible now? Yes. Okay, good. So what I have done is, I am saying that this is basically, you can use the zigzag method that we discussed in class. Apply that zigzag method, that is top to down, left to right. You are going to fill the states in a cyclic order. Q0, Q1, Q2, Q3, Q4, Q0, Q1, Q2, Q3, Q4. And the number of states are going to be 4 because you are dividing by 5. Why? Because you are going to get remainder 0, 1, 2, 3, 4, and 0 and 1 are basically your inputs. And every state you are going to assign an input, an output. So over this, say on this state you are going to print 0, on this state 1, on this state 2, on this state 3, and on this state 4. So this is basically the Murray machine, right? So let's talk about Mealy machine also. So draw the Mealy machine for 1's complement, for 2's complement of a number. Murray machine for 2's complement of a number. Yes, Murray machine for 2's complement of a number. Yes, Saptak, very good. So how do we draw the Mealy machine? Till the time zeros are coming, we stay here, we replace them with zeros. When a 1 comes up, you replace that 1 with a 1, and after that every 0 has to be changed to 1 and every 1 has to be changed to 0. That's it. This is how we draw the Mealy machine for 2's complement. How do we do that? How do we construct this? So let us take one number. How do we calculate 2's complement? First we take the 1's complement. So 1's complement will be complement every bit, and 2's complement will be add 1 to it. 1 plus 1 is 0, 1 plus 1 is 0, 1 carry, 1 plus 1 is 0, 1 carry, then 1, and then 0, 1, 1. So till the time you are getting zeros, you are going to replace them with zeros. Once you get a 1, you replace it with 1, and after that you are going to complement the number. So this is how it is being done. After that you are going to complement the number, so that is why you are going to get this kind of machine, Mealy machine. Right? Is everyone fine till this point or not? Tell me, guys. Is it clear or not? Is it clear or not till this point? Mayank is okay. What about others? Abhilash, Saptak, Sovik. Who else was there? Kirti. So no, there is no final state here. Saptak, there is no final state here. There is no final state here. Okay? Good. Okay, so you see the tuple, right? You saw the tuple. Where is the tuple? Here it is. There is no final state in the tuple, right? Okay, let's move ahead. So how do you convert Murray machine to Mealy machine and a Mealy to Murray? So while going from Murray to Mealy, move the output. So Murray has the output on the state, Mealy has the output on the transition. So from Murray to Mealy, when you have to do, move the output to the incoming transition, and hence the conversion is done. Move the output to the incoming transition, that's it. For Murray to Mealy conversion, what we have to do for Mealy to Murray conversion? What do you do for Mealy to Murray conversion? What do you guys do? Tell me. So what does Mealy has? Mealy has the output on the transition. We have to move the transition to the output from the transition to the state. Right? We have to move the output from the transition to the state. Right? Okay? So we have to move the output from the transition. So move the output from the transition to the destination state. That's it. So for example, while doing this, what might happen is that transition, so for example, it might happen that two incoming transitions to a state has different outputs. What do you do that in that case? What do you do in that case? Definitely, very good, Saptak. The number of states are going to increase. If there is a conflict, split the state. That's it. If there is a conflict, split the state. That's it. ठीक है? If there is a conflict, split the state. Is everyone fine? Did it got refreshed or brushed up or not? Tell me. Okay. Very good, very good. Others, please tell me, is it okay or not? Saptak is okay. Abhilash, Souvik, Mayank, Kirti, tell me. Adish. So Adish wants one example on this. Okay, so let's take this example. Convert this Mealy machine to Murray machine. Convert this Mealy machine to Murray machine. So you have this Mealy machine with you, you have to convert it into a Murray machine. Let me call it as state A and this is state B. Tell me the number of states in the Mealy machine. So when you convert it into Murray, tell me the number of states. Yes, very good, Saptak. You are going to get 3 states. How? So you move this output to the incoming state. So this becomes A0. And like this. But when you are moving the outputs to this state, this is making it as 1, this is making it as 0. So we will make 2 states, one with B0, other with B1. We'll split this state and we are going to get 3 states. And then you can fill up the transitions based upon looking at the original. By looking at the original one, you can fill it up. How? Like this. Now A on 1 goes to B1. A on 1 goes to B1. So B on 0 goes to B1. B on 0 goes to B1. And B on 1 goes to B0. That's it. Is it okay, Adish? This is how you convert. Adish, is it okay? Yes, we have split it. We have split it up. Okay, good. So let's move ahead. The next important topic that is there in our syllabus is regular expressions. And regarding regular expressions, what is the question that we get mostly is basically, given a language, what are the regular expressions that are going to represent it? So the only concept which comes in mind. So for the regular expressions, I always say the question is of aptitude, not of the theory of computation. And what is the aptitude that is to be used over here? That is, the strings in the language should be accepted and strings not in the language should be rejected. Apart from this, you only need to remember some identities, that is which I am those identities I am stating over here on the board. Okay, what are the identities? Phi dot r is basically nothing but r dot phi is nothing but phi. R plus phi is nothing but phi plus r plus is nothing but r. Epsilon dot r is nothing but r dot epsilon is nothing but r, right? And then we have phi star is epsilon, epsilon star is also epsilon, right? These are few of the identities. Then what is r star? R star is r plus. R plus is basically r dot r star. These are few of the identities that you should keep in your mind. Apart from this, it is all about it is just a business of aptitude. It's not at all theory of computation. Although it is theory of computation, but the the marks are free for the aptitude part. Okay? So just keep this thing in mind. Strings in the language should be accepted. Strings not in the language should be rejected. And strings not in language should be rejected. That's it. Okay. So let me write one more identity that is important. That is a plus b star. What it is? It is equals to a star plus b star whole star. It is also equals to a plus b star whole star. It is also equals to a star plus b whole star. It is also equals to a star. Yes, this is done. This is also equals to a star b star whole star. This is also equals to a star b a star whole star. A star b a star whole star. Or b star a b star whole star. Yes. And it can also be written as a star b whole star b star, or it can also be written as b star a whole star b star. So this is all a plus b star, right? Just keep all this in your mind. Is everyone fine till this point or not? Tell me. Adish is okay, Mayank is okay. What about others? Please tell me. Yes, everybody okay? Okay, good. So let's move towards grammars. So we have some 3 types of grammars: type 3, type 2, type 1 and type 0. Tell me what is the format of type 3 grammar? It is called? So Saptak says, sir, please explain how the last 2 steps are equal to the first step. Which step? Which step, Saptak? Are you talking about identities? Are you talking about identities, Saptak? So just let me know your question in more detailed form, Saptak. So type 3 is basically regular grammars, and what is the format of regular grammar, guys? This is regular, this is context free, this is context sensitive, and this is unrestricted. Or also known as phase structured grammar. Phase structured grammar. What is the format now? So Saptak, which part you are saying? Are you talking about identities or the Murray to Milley conversion? Just let me know the complete question. So then it is A goes to alpha B beta, or it is also A goes to B alpha beta. This is left linear, this is right linear. Right, over here it is just A goes to alpha. Over here it is alpha goes to beta, and over here it is also alpha goes to beta. Right? But over here mod of alpha has to be less than equals to mod of beta, that is you are going to expand every time. Right? You are going to expand every time. And if you see this, what is A? A is basically vertex. B is also vertex, or you can call it non-terminals. What is alpha and beta? Alpha and beta are a terminal star. What is A over here? It is a non-terminal. What is A over here is non-terminal. What is alpha over here? Alpha is basically V union terminal star. Now what is mod alpha? What is alpha and beta over here? Alpha is basically V union terminal plus, and beta is also V union terminal plus. And when we talk about type 0 grammar, it is V union terminal plus, and over here it is V union terminal star. Over here it is V union terminal star. Right? Is it okay, everyone? Yes. So Saptak asked about the identities. Okay, Saptak, there is one more identity through which I converted the last part. So there is an identity which says that this expression is equals to this one. Through that you will get it. Right? And you can take certain examples and prove this. Okay? So use this, you will be able to get the last part. Okay, Saptak, is it okay? Good. So till this point, everyone on the same page or not? Tell me, guys. So this is all about grammars that you should keep in mind while going to the exam. Okay, good. So let's move ahead to the next topic. So this completes finite automata as a whole, what is more important, what is further important is push down automata. So let's move towards push down automata. Now tell me what is the 7 tuple for push down automata? 7 tuple for push down automata. Q sigma delta Q naught F. What else? What else? What else do we have? Stack is there, very good. But stack, how do we write stack? Push and pop is there. But these are operations, I am talking about tuple, Adish. Yes, very good. So, Abhilash, we call it bottom of the stack, right? Z0 is bottom of the stack. This is Z0, and then we have the stack alphabet, tau. So, this Q remains the same. Set of states. Now, sigma is set of alphabet, or basically the alphabet. Your Q delta is basically what we are going to discuss. Q naught is your initial state. Same thing. This is basically set of final states. Z0 is basically bottom of the stack. This is to tell you that you have reached the end of the stack, and tau is basically your stack alphabet. Now, when I talk about PDA, okay. When I talk about PDA, DPDA, tell me what is delta? What is delta for a DPDA? Tell me what is delta for a DPDA? Yes, good Kirti, it is Z0, very good. Tell me delta for DPDA. Tell me delta for DPDA. Yes, Aman, good evening. So, what is the delta for DPDA, guys? So, Q cross sigma cross tau goes to what? Q cross sigma cross tau goes to what? Okay, very good, Abhilash. Perfect. Even Saptak, there is a slight mistake. So, over here your delta is Q cross sigma union epsilon cross tau goes to Q cross tau star. And when I write it for NPDA, what is the change? It becomes Q cross sigma union epsilon cross tau goes to Q 2 raised to power Q cross tau star. That's the change. Is it okay? Right, everyone? Right? Are you able to recall this or not? Tell me. Good, I think 3 of you have answered it correctly. Those who could not recall, now you can just recall. Now you tell me, let me draw the DPDA for a to the power n to a to the power n b to the power n greater than equals to 1. This will help you in just refreshing how do we do it. So what will you do? in accepting a to the power n, b to the power n? You will push a's, yes Kirti, you are correct. So you will push a's, and then for every b you are going to pop one a. That's what you have to do, right? So how do we do that? Okay, so whenever a comes in, you are going to push it, right? You push it in the stack, and whenever a b comes up, you pop it. That's it. That needs to be done. So how do we do that? You are initially at q naught, and when an a comes in and the top of the stack is z naught, when an a comes in, when the top of the stack is z naught, you are going to push a z naught. When an a comes, when the top of the stack is a, you are going to push a. That's it. A's business is done. Now when a b comes up, and the top of the stack is a, you are going to pop a. And on this state, this is q1, let's say, if b keeps on coming, you are going to pop a's further. And at the end of it, if you reach epsilon, that means the end of the string, and the top of the stack is z naught, then you are going to replace it with z naught, and you are going to reach the final state. Let us call it q2. This is how you make DPDAs. And while talking about NPDAs, you are going to have two transitions for the same a z naught, right? On a given state, on a given alphabet, on a given stack top, you are going to have more than one transitions, right? You are going to have more than one transitions, right? And now when I say more than one transitions, again the determinism over here that we are having in DPDAs is basically called partial determinism, because I have only told what happens on a z naught. What happens, so on this state I have told what happens when an a comes and z naught is at the top of the stack. I have told what happens when an a comes when a is on the top of the stack. I have told that when b is the input symbol and a is on the top of the stack. I have not told what happens when a b comes and z naught is at the top of the stack. I have not told about it. I have not specified it. Therefore, this is a partial determinism. So in partial determinism, you either mention at max one transition for every given combination of q cross sigma cross tau. So this is partial determinism. This is partial determinism. And when we go to NPDAs, you may have the liberty to write more than one transitions on a given combination of q cross sigma cross tau, right? Is it okay? Right, everyone? So now let's move towards, let me give you one more question to solve and just check whether you understood DPDAs or not, whether you recall DPDAs or not properly. Draw the DPDA for a to the power n, b to the power m, a to the power and c to the power n plus m. ठीक है? Tell me, report the number of states. Right, and where n comma m is greater than equals to 1. Tell me the push down automata for this language. Tell me the minimum number of states. Right, is the question clear, everyone? Is the question clear or not? So you guys solve this question. I'll be back in a minute. Yes, guys. So Abhilash says can be 4, but 3 is minimal. Okay, good. So Abhilash says can be 4. Okay, let me start read from the beginning. Kirti says, so I think push A, Bob bhi theek hai. Saptak says 4 states. Adish says 3 states. Is it audible, guys? Just tell me. Is it audible now? Saptak says 4 states. Adish 3, Kirti 3, Mayank 3, Abhilash 3. Might be 4 too, sir, but I want a minimal one, Adish, right? So Sovik says 4. Abhilash says can be 4, but 3 is minimal. Adish, how one extra transition for final state, right? Adish says, okay, you guys start talking to each other. Good, good. So Abhilash says push A and B on initial state, push B for C, go to second state, then loop with B and A with C, right? Okay, yes, we have a stack, so we cannot come back again. Got it. Abhilash says then go to final state with epsilon. Yes, it is possible. Okay. Yes, everyone. Is my voice audible or not? Just can somebody confirm, is it audible or not? Okay, good, good. So again, yes, I think you guys have come to a mutual consensus after discussion on the chat. But just for the sake of completion, let me just simply draw the automata. So basically, on A on Z naught will give you A Z naught, and A on A will give you AA. On the same state, you can also have transitions for B. B on A will give you BA, and B on A, B will give you BB. Then you will have C. C on B will give you epsilon. Then C on B will give you epsilon, and C on A will also give you epsilon. And then finally, epsilon Z naught will give you the final state, right? Is it everyone has the same DPDA? So why I could do this? Because now somebody might have an issue, because can B be followed by A? This will not be able to reject, this will be able to reject. Because if an A comes, I do not tell what happens if there is B on the top of the stack. That configuration is already dead here. That's the important crux of this question. So somebody might ask that A and B, after B and A can come. No, it cannot come, because when an A comes after that, B will be at the top of the stack, and I have only specified it for Z0 and A. I have not specified it for B. Is it okay, everyone? On the same page or not? Tell me, guys. Okay or not? Okay, good. So next topic is Turing machines. So again, Turing machines gives us one extra benefit. So DPDS gave us stack, and Turing machines gave us infinite tape, and also the writing capability. I can move left and right. That is one thing that I can do with the Turing machine, and I can also read as well as write. And there is a finite control along with the in the Turing machines. So okay, so what is the 7 tuple for Turing machine, guys? What is the 7 tuple? What is the 7 tuple for Turing machine? What is the 7 tuple for Turing machines? So it is Q sigma delta Q naught F, and then we have a blank as well as tape alphabet, which is tau. And this Q is again same thing. This is the set of states. Sigma is alphabet. Q naught is initial state. F is set of final states. Delta we are going to discuss. B is blank. T is tape alphabet. T is tape alphabet. Right? So what is the delta? Very good, Abhilash. So what is delta for deterministic Turing machine? So delta for deterministic Turing machine will be Q cross tau goes to Q cross tau cross left or right, and delta for non-deterministic Turing machine will be q cross tau to 2 raised to power q cross tau cross left slash right. Okay? Very good, Kirti. This is how it is. Right? Okay, I hope everybody could recall the point. Right? Is it okay, everyone? Yes. So let us draw just one Turing machine also. That will give you the picture at how to draw them. Let us draw the Turing machine for a to the power n, b to the power n greater than equals to 1. How do we do that? N is greater than equals to 1. Okay. So n is greater than equals to 1. How do we do that? So just we keep this thing a, b, b in our mind and then draw the Turing machine. How do we do that? We start from the initial state on finding an a. So how do we do that? We keep on replacing a's with x's and b's with y's. Right? This is long process. Yes. So how the questions can come? They can, put a question mark on any transition. Same goes for PDAs also. We can put question marks on the transitions and ask what is going to happen in that transition, right? They can ask that what is going to happen with that transition, right? So let us draw this. So we are going to replace a's with x's and b's with y. So initially, if an a comes, I replace it with an x and then I move right. After that, if a b comes up, I'll replace that with a y and move left. Now if in between a's come up, I keep on replacing them with a's and keep going right. If y's come in between, I replace them y's with y's and keep on moving right. After that, if while moving left, I might find a's on the way and also y's on the way. So how will I do? I will keep on replacing a's with a's and keep moving left. I'll keep on replacing y's with y's and keep moving left again. When will I stop? When I reach x, I get to know I have seen this, now I have to see the next a. So when you reach x, by doing this, you replace x with an x and you move right. And you move right. Right? Once you move right, you will find another a and you will repeat the same process. You will replace this x with a with x and this a with y, this b with y. And over here there is a blank, over here also there is a blank. Now what to do next? What to do next? Now over here, when you reach this time, you will never find an a after this. You will find a y. So when you reach after this, at this point, you will find a y, not an a. So in this case, if you find y, replace y with a y, keep on moving right. Keep on replacing y's with y's, keep on moving right. If eventually you find a blank, you replace blank with a blank and then you move either left or right, doesn't matter, I reach the final state. I reach the final state. Okay, everyone? Is it okay? Tell me whether it is okay or not. Good, 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 Kirti, good, Mayank. Right, so Mayank is okay, Kirti is also okay, and Saptak is fine, Souvik is fine. Abhilash, is it okay till this point? Should we move ahead? Yes, okay. Is it okay till this point? Yes, okay. Let's move ahead. So I think the next important topic that is comes is identification of the type of the language. Okay. That's fine. So identification of the type of the language. So for that you should have the Chomsky hierarchy in your mind. You should have Chomsky hierarchy in your mind. So you should have Chomsky hierarchy in your mind for solving this. Questions on identification of the type of the language. And I hope you know that regular languages are a subset of context-free languages, context-free languages are a subset of context-sensitive languages, and context-sensitive languages are a subset of recursive enumerable languages. Right? And regular languages are regular languages are accepted by regular languages are accepted by finite automata, and they are generated by type 3 grammar or the regular grammars. So type 3 is regular, type 2 is context free, type 1 is context sensitive, and type 0 is unrestricted. We have already seen this point. Now what does a grammar does? Grammar generates the language, acceptor accepts the language, and the language is itself. So context free is accepted by push down automata and generated by context free grammars. context sensitive is generated by context sensitive grammars, and recursive enumerable is generated by unrestricted grammars. And they are accepted by linear bounded automata and Turing machines respectively. Is it okay? So all this is just, you just need to recall all this, and this much is, I hope everybody recalls this. So Kirti always makes mistakes in understanding context free and context sensitive. I hope it is fine now, Kirti. So all the telegram questions you make mistakes in context free versus context sensitive. Is it okay now, Kirti? Yeah. So let's move ahead and talk about how do we identify if the language is regular. Yeah. Yes, people, tell me, how do you know that a language, given language, is regular or not? How do you check that? How do you check that the given language is regular? How do you check that the given language is regular? Finite, infinite, but has a pattern. Okay, very good, Avilash. So let's just quickly refresh it. So regular languages are the ones which are accepted by finite automata. First of all, that's the most important point. All the finite languages are regular. You can write down states for every string in the language and then minimize it, right? Then, so for example, set of all two length strings, a b, b a, b b, a raised to power p, p is prime when p is less than equals to 100, again finite language. A raised to power n, b raised to power n is greater than equals to 0, n is less than equals to 1000, again finite language. But for infinite language which require no memory or finite memory or no comparison or finite comparison, they are going to be regular. So for example, a star, b star. What is this? A star, b star. So a star, b star is definitely regular. There is no comparison needed, right? And the other important point which Abhilash correctly mentioned is that pattern has to be in AP. A raised to power n square is not regular. The pattern has to be in AP because you have states. So you can go and loop back. So whenever you loop back, you can have a common difference. You cannot square, right? So that is why infinite languages with pattern in AP are regular. So for example, a to the power 2n is regular, a to the power 3n plus 1 is regular, but a to the power n square, a to the power n factorial, a to the power 2 raised to power n, all this is not regular. All this is not regular. Next is infinite languages requiring infinite memory comparison are non-regular. So for example, a to the power n, b to the power n. This is non-regular because you require comparison. You have to compare the number of a's with number of b's, and you have a finite memory which is in the form of states. So therefore, this is non-regular. So if it is non-regular, then what it is? It is context free language. It is a context free language, right? So now let's talk about context free languages. What are context free languages? They are accepted by push down automata. So they are accepted by push down automata. So push down automata allows infinite memory and counting, but that infinite memory and that counting has to be one infinite comparison at a time. Very good. Further, no more than one infinite comparison should be made at a time. So you have to make one infinite comparison at a time, right? So for example, a to the power n, b to the power n, here you are doing one infinite comparison at a time, therefore it is context free. But if you are doing two infinite comparisons at a time, a to the power n, b to the power n, c to the power n, you are comparing number of a's with number of b's, you are comparing number of b's with number of c's, you are doing two comparisons at a time, this is not context free. Why it is like that? Because when you push a's, then for b's you pop it out. What you have to do for c's? How would you compare c's? right? So that is why a to the power n, b to the power n, c to the power n is not context free. Now WW is also not context free. Why? Because when you push W in the stack and when you want to compare it with other W, you have the last letter of W, last alphabet of W at the top, last symbol of W at the top, and you have to compare with the first symbol. You have to compare with the first symbol. Right? For example, W is ABB, another W will be ABB. You push ABB at the stack, ABB. Now if now next ABB, I want to compare this A with this A, but with the stack I can't do it. You can only pop the last element. It is last in, first out. Okay? Right? Is everybody getting this or not? Tell me. So I am doing it faster because we have already done it in the class. Yes, good. Okay, context free languages. Again, if we can design a deterministic PDA, we call it DCFL. If we can design a non-deterministic PDA, then the language is just CFL. It is not deterministic CFL. Right? So for example, WCWR, it is deterministic CFL. And WWR, it is just CFL. Why? Because I should know when to push and when to pop. In WWR, I do not get to know that when to push and when to pop. So in WWR, I do not get to know when to push and when to pop. Right? But in WCWR, I get to know until C comes, you have to push, and after C, you have to pop. So therefore, WCWR is DCFL, and this is just CFL. So this is context free and regular. What about context sensitive? What about context sensitive languages? So when you want to do more than one infinite comparison at a time, then comes the context sensitive languages at rescue. So accepted by linear bounded automata, some examples are, these are the examples. A to the power n, why? What is linear bounded automata? It is Turing machine and the tape size is restricted to the size of the input. Tape size is restricted to the size of the input. Right? Okay. So I have restricted the tape size to the size of the input. Now, if I have to accept A raised to power n, B raised to power n, C raised to power n, how will I do? Just like Turing machine, I made the Turing machine for A to the power n, B to the power n. I never went out of the bounds. For A to the power n, B to the power n, C to the power n, or what I'll do, I'll replace A's with X, B's with Y, and C's with Z. And I'll be able to make a Turing machine which will only use the size of the tape that is equal to the size of the input. It will not go beyond that. So therefore, it is a linear bounded automata. It is accepted by LBA, and therefore it is context sensitive. Same goes for WW. Same goes for A to the power n, B to the power n, C to the power n, D to the power n. Even you write E to the power n, F to the power n, Z to the power till Z to the power n, everything will be accepted by linear bounded automata. Right? A to the power n factorial, n square, 2 raised to power n, all are accepted. A to the power p, p is prime. You do not require the length of the string greater than the size of the input while accepting these languages. So therefore, all this is context sensitive languages. Right? That's all. That's all about identification of the type of the language. If you can just brush up this much concept, you will be able to solve all the questions. Right? Okay, everyone. So let me give you just one question on to check whether you understood it properly or not. So tell me Which of the following are regular? Tell me which of the following are regular. Good, Abhilash, good. So Abhilash, you are correct. What about others? Yes, all of you are correct. Very good, guys. So you have mastered identification of the type of the language. You will definitely be able to crack the question which comes in exam. So when you are looking at this language WXW, so how do we solve such questions? We always try to take the worst case in which we are trying to reduce the number of comparisons as much as possible, and we should also remember that it is the basically the language is a union of all the cases, and if the worst case that we take in which the comparisons are least, if that subsumes all other cases, then we say that the language is regular. So let us take this example. In this case I can say that my W can be epsilon and my this W can also be epsilon. My this W can also be epsilon, so my X becomes A plus B star. This is regular, therefore this is regular. Right? And the same goes for this example also. This is epsilon, this becomes A plus B star. Yes, A plus B star. So this is also regular, right? Okay. Now over here, in these two examples, what we are doing is, let us take the length of the string as W as 1. If I take W as 1, in this case I can write the expression as A comma A plus B plus A plus B comma A plus B plus B. If I write this can be the expression when I consider W as of length A. When I consider W of length A. So when I consider W of length A, now this case does not subsume other cases. That means if I take length 2, if the length is 2, then it will be A plus B plus AA plus BB A plus B plus BB plus AB A plus B plus AB plus BA A plus B plus AB BA. Now if you see, this case is being subsumed by that case. Why? Because I can take it like this. Even this case is also subsumed above, but this case is not subsumed above. It is starting with A and ending with B. So since it is not being subsumed, this is incorrect. This is incorrect. But what about this case? In this case, I can write this expression very well. I can write this expression very well. How? How? Let me write down the expression for two length strings. This is the expression for one length string. If I write down the expression for two length string, it comes out to be A plus B plus A plus B plus AA plus AAB, A plus B plus BA plus BB, A plus B plus BB, or BA, A plus B plus AB. AB. Right? Now if you see, this first case subsumes everything. First and last letters are same. So now therefore this is regular. Therefore this is also regular. Therefore this is also regular. So the answer will be A, C and D. Is it okay everyone? So the answer will be A, C and D. I hope everyone is clear. Just type in. Yes, yes, good Saptak, good Mayank. Sovik is also okay. What about others? What about others? I've taken an example, okay. What about others? Please tell me if it is okay or not. Okay. Yes, everyone clear? Very good guys, very good. So now let's move to the next topic, that is decidability, and after that we'll do about closure properties, and that way we will end the session. Right? So just only two topics are left, that is decidability and closure properties, and we'll just refresh the table of closure properties and decidability properties, and we'll just try to recall how do we remember this. How do we remember this? That is what we are trying to recall. Right? So let us see. So let me make a table for decidability. I need to draw a table. Do we have table here? Just let me check. If we have a table, we can directly take the table from here. No. Shapes text. Okay. One, two, three, four, five. 3, 4, 5, 6 languages and some 3 rows. 1, 2, 3, 4. So 1, 2, 3, 4, 5. Yes. So let me write it down. Okay. So maybe I'll just take it a bit here so that. Okay. So what are the types of languages that we have? So we'll write the types of languages here first. So we have some regular languages, then we have deterministic context free languages, then we have context free languages, then we have context sensitive languages, then we have recursive languages, and then we have recursive enumerable languages. Right? Right, everyone? And these are the properties which we are discussing for. These are the properties which I am discussing. Right? Okay? So I'll just make copies for this because I'll need it for various times. I will need it 1, 2, 3. I have 4 of them. I will require 1 more. 5. Okay. Great. Here we go. Just a second. Yeah. You're on slide 39. One, 2, 3, 4, 5. Right. So 1, 2, 3, 4, 5. I have 5 of them, is it? One, 2, 3, 4 I have. I want just one more. One, 2, 3, 4, 5. Correct. Now we are correct. Okay. So yes. So regarding decidability, yes, thank you, Vipin sir. So so when do we say that a property is decidable, guys? Tell me, when do we say a property is decidable? When do we say that a property is decidable? Emptiness. When do we say that a property is decidable? Yes guys, please reply, tell me. When do we say property is decidable? Yes. Yes, thank you Pratik sir. So when do we say that a property is decidable? Tell me guys. So we say that a property is decidable if we can write an algorithm for the same. If you can do that, then we'll say that that property is decidable. Right everyone? So we'll have some 5 properties over here. What does membership means? What does membership mean? Does string belongs to the language or not? What does emptiness mean? What does emptiness mean? Okay, so let me write down all the properties first and then we will define each property and say what happens for each language. So next is L1 intersection L2 is phi or not. Then is L finiteness. Then we have L1 intersection L2 is phi, finiteness, then complement is closed, then intersection is closed, and then last is L regular. These are the properties that we study. These are the properties that we study, right? So yes, Saptak, Sovik, Kirti, Mayank and Abhilash, tell me, when do we say that a property is decidable? When do we say that a property is decidable? Yes, tell me guys. Right, exactly. So when we can write an algorithm for it and that algorithm stops in finite amount of time, then we can say that property is decidable. Okay, Sovik, no issues. We'll do it in the class also in detail, but over here you will just get an overview, Sovik, right? Because this is a revision session. Language, not language, Kirti. That property, you should be able to write an algorithm for that property, right, Kirti? Okay? Is it okay? So now let us define each property now and then we will what is this color? Okay, let me use this one. Okay, so membership means does the string belongs to the language or not? That is membership. Now emptiness is language phi, completeness language is sigma star, equality is L1 equals to L2, subset is L1 a subset of L2. Whether you can write these algorithms for all these kinds of languages, that is what is being asked, right? Then we have L1 intersection L2 is phi. It's very clear. Finiteness is basically when is the language finite or not? Is the language finite or not? Complement closed or not? So is the complement closed? Can we write an algorithm for this? So for example, when we take a complement, are we going to get the regular language again? Is this property decidable or not? Similarly for intersection and similarly last is L regular. So given a context free language, it can also be regular because context free language is a superset of regular languages, right? So therefore, let us try to remember what it is. So tick means decidable and a cross means not decidable. So if you just revise this much table and have this much table in your mind, all the questions in the GATE exam you will be able to crack. Not an issue. So for regular languages, all the properties are closed. All the properties are decidable. ठीक है? For recursive enumerable languages, all the properties are not decidable. Only one property is decidable, that is intersection is closed. That is intersection. Right? Only one property, that is intersection, is closed, otherwise it is undecidable for all. For CSL and recursive, the behavior is exactly similar. So you just have to remember the points which I am speaking. So there are some 60 cells. You don't have to remember 60 information. You just have to remember what I am speaking. For regular, everything is closed. You don't have to remember 10 cells. You just have to remember just one fact. Now for recursive enumerable, I am telling only one thing is decidable, that is intersection is closed. Now for CSL and recursive, you have to remember that they have the same behavior. And they are only decidable for three things, that is membership, complement and intersection, except that they are not decidable for anything else. They are not decidable for anything else. Right? Now let's come to DCFL and CFL. Right? DCFL and CFL. So DCFL stands for deterministic context free languages, CFL is context free languages. Now tell me for DCFL and CFL. For CFL, only three things are decidable: membership, emptiness and finiteness. Rest everything is undecidable. And in the class we have already done the proof for the same, through which you will remember that. Membership, emptiness and finiteness. Sorry, for the CFLs, not for DCFLs. Let me recorrect it. That was for CFLs. For DCFLs, two more things are decidable. That is, complement as well is L regular or not. This is also decidable. Right? So, yes. And apart from this, even completeness is decidable. Even completeness is also decidable. Why? Because emptiness is decidable, complement is decidable. What is the complement of emptiness? Completeness. So for DCFL, apart from what is CFL is decidable, it is also decidable for finiteness, for complement, for L regular and for empty and for completeness. Is it okay? Yes guys, just remember, just brush up this point. So Abhilash says DCFL subset intersection is equals to 5, intersection is closed, is undecidable. Yes. So even equality is undecidable, Abhilash. Equality is undecidable as well as intersection phi and intersection, right? Even equality also, Abhilash. Subset intersection phi, intersection is closed, this is undecidable, as well as equality. Okay? So 4 things are undecidable, everything else is decidable. 1, 2, 3, 4. Yes. So I hope everyone fine till this point. Yes, tell me, is it okay? So maybe if you want to note it down, so what you can do is you can watch the video again later and just take a snapshot, and maybe you can also take a snapshot also right now if you want. So what I'll do is I'll stop on the count of 5. I will change the slide. On the count of 3 I'll change the slide. Okay, if you want to take a snapshot you can take. So 1, 2 and 3. Again on the count of 3 I'll change the slide. If you want to take a snapshot you can take it. So 1, 2 and 3. Okay, so this is all about decidability. Let's talk about closure properties. Let's talk about closure properties. So what do we mean by a language is closed under a property? What do we mean by it? Closure properties. Closure properties. Tell me, what do we mean when we say that a language is closed under an operation? This you know through DMGT also. So what do we mean by a language is closed? No. Yes. So language does not remain same. You come back to the same type of language, Kirti, right? So for example, if you take the complement of a regular language, you are again going to get a regular language. If you take union of two regular languages, you are going to again get a regular language. If you take a intersection of two regular languages, you are again going to get a regular language. If you take a reversal of a regular language, you are again going to get a regular language. So after applying that operation, are you coming back to the same class or not? That means that you are closed. Is it okay, Kirti, right? So even again, Mayank, not same result, same type of language, right? The class should remain the same, Mayank, right? So let us write down the closure properties also, the table for closure properties also. What is the first property? Union, intersection. Then we have set difference. Then we have complement. Then we have intersection with a regular language. Okay. So then we have intersection with a regular language. Then we have concatenation. Then we have reversal. So not reversal, first comes clean closure. Then we have clean plus. Then we have reversal. Then we have subset. Then we have homomorphism. Then we have epsilon free homomorphism. Then we have inverse homomorphism. Then we have substitution. Then we have epsilon free substitution. Right? So these are the properties which we discuss. So let us talk about each property, about each language. So first of all, regular languages are closed under everything except subset. So subset is not closed for any language. Subset is not closed for any language. And regular languages are closed for all the operations except subset. Okay. Except subset, they are closed for all the operations. Right? Now, let's talk about recursive enumerable. So they are closed for everything except set difference and complement. Otherwise, they are closed. So let's talk about CSL and recursive. For CSL and recursive, they are having the similar behavior, just like decidability. So over here, tick means closed and cross means not closed. Okay? So for CSLs and recursive languages, so they are closed under all the operations except homomorphism and substitution. Except homomorphism and substitution, they are closed. Right? Okay, Kirti, I'll get back to you on this. Just let me complete the table. Right? So let's talk about DCFL and CFL. So for DCFL and CFL, what is the thing? So DCFLs are not closed under intersection set, CFLs are not closed under intersection, set difference and complement. We have done the proofs for the same in the class in detail. Intersection, set difference and complement, they are not closed under these operations. Except that they are closed. Next is DCFL. So DFAFLs are not closed under any of the things except they are closed under three things. Let us see what are those three things. They are closed under complement and intersection with the regular language and inverse homomorphism. Except that they are not closed under anything. That's it. Right? So this is all about the properties which you should keep in your mind. And if you remember this table, believe me, you'll be able to crack any gate question that comes. So now let's go back to Kirti's doubt. She says, sir, homomorphism includes sir, does homomorphism include homomorphism and epsilon? No. So homomorphism means you are going to replace sigma with tau star, but you do not take epsilon. When in the homomorphism you allow epsilon, taking tau, taking epsilon also, then it is called epsilon. Then it so homomorphism means epsilon is also allowed. Epsilon from homomorphism means epsilon sigma goes to tau plus. Epsilon is not allowed. Is it okay, Kirti? Epsilon free means epsilon is not allowed. Replacing with epsilon is not allowed. Okay, Kirti? So this is homomorphism and this is epsilon free homomorphism. Right? So I hope if you remember this table, you should be good to go. And what is substitution? When you replace sigma with a language, this is substitution. Right? So this is all about closure properties. Right? So I hope you understood this. So maybe if you want to take a snapshot, I'll just count 3 and then you can take a snapshot for the same. So 1, 2 and 3. 3 seconds for this, 1, 2 and 3, and another 3 seconds for this, 1, 2 and 3. Yes. So that's all about the quick revision session on theory of computation. And what I tried is to take you through the entire subject, which we did in somewhere around 60 to 65 hours in some 3.5 hours. What is left? This was the last one, Souvik. Right? So 15 properties we study. Right, Souvik? So in this 3.5 hour session, or 3 hours 45 minutes session, what we did is we tried to cover almost everything which we covered in class in a way that we just brushed up those concepts. So if someone has not attended the classes, it might have been difficult for him or her to understand it in this speed, but the purpose of this lecture was completely, I could not take the snapshot of the last one. Okay, so this one, Souvik? This one, Souvik, are you talking about this one? Yes, you can take it now. 11 to 15. So this one, yeah. 11 to 15, this one. Yes, you can take it. Okay. So now, as I said, if I think this is how I could have done, to cover everything in what we studied in the class. And if you remember this much on the last day, I think you'll be able to crack everything in the GATE exam too. So again, as I said, just 21 days are left now, and if you count today is gone, so then it is less than 21 days also, it's 20 days. So just remain focused for the remaining days, guys, and what you have to do is just keep on revising, keep on doing GATE PYQs, and keep on attempting the mock test series. That should be enough to crack whatever comes up, right? And just remain confident, and you don't need to worry, and just try to improve yourself. Okay, don't compare yourself with others. This is not the right time to do that. Okay, so just keep on focusing what you already know, just keep on revising what you already know, because it is very important to recollect what you know, because nothing can be worse than that if you knew a concept but you could not recall it in the exam. So that is why it is important to revise, keep on revising till the last day, right? So everything will be good. You all have done, already have put a lot of effort, just a last inch is required, right? So I'll see you tomorrow again with the session on compiler design at the same time from 5 p.m. onwards, right? I hope all of you could, brush up all the concepts that we study in TOC, right? Okay, everyone. So should we close the session? I hope you all enjoyed the session and also understood. Tried to, recapitulate everything what we studied in class. Yes. Okay. So, okay, good night, guys, and all the best for the exam. See you guys. Good night.